now I close my introduction, and I will invite Robert to talk. Yes.
Excuse me. I forgot to mention that after the Q&A session, we would like to take a picture with the audience, so don't go away, stay with us, because I'm not sure if you're having the picture in the room or just outside, but we would like to have all of you in the picture. Thank you. And of course now we welcome Robert Zubrin and illustra. Thank you.
All right. Can I have my charts?
Sure.
Hold on.
You can advance with this one, and this is the last one.
Thank you. Okay. Thank you, Antonio, for that introduction, and to the Italian Space Agency for inviting me, and to all of you who have decided to come to hear what we have to say. I'm going to talk about how I believe we can get humans to Mars within a decade. Okay? And so as to give you a broad picture of my vision on how this can be done. And in the course of this, though, I'm also going to mention a number of concrete actions that the Italian Space Agency could take within the next couple of years that would be significant steps towards this, contributing to it, and to our knowledge of Mars and space exploration in general, and also broaden public participation in space exploration profoundly. But let's talk about the big picture first. Okay. Humans to Mars in a decade. If you've seen NASA's plan, that's not possible. Okay? Giant interplanetary spaceships powered by ion drive engines based at lunar orbiting space stations. Okay? A whole new parallel universe will be built, and then in that new universe, humans will go to Mars. Okay? This is not happening in 10 years. And I would argue that it is not happening. Okay. Period. This is not really a plan to go to Mars. This is a plan that is used to justify a variety of technology development programs by providing some dramatic visionary utilizations for them in the future. But this is not a real plan to go to Mars. We do not need giant interplanetary spaceships to go to Mars. We do not need lunar orbiting spaceports to go to Mars. And we certainly don't need giant interplanetary spaceships based at lunar orbiting spaceports in order to go to Mars. Okay. What we need to do to send humans to Mars is send a small payload capable of supporting a small group of people from Earth to Mars, and then sending either that or a comparable payload back. Okay, so it's not about realizing the vision of the science fiction future. It is about sending payloads. Okay. Now, the payloads are of a scale, I'll talk about this later, where we need a heavy lift vehicle. A vehicle comparable in power to the Saturn V. This is 1970 you're looking at. Okay, this is what the ancients were able to do prior to the Dark Age. But now we are experiencing the Renaissance, and capabilities comparable to this are being created once again. In this case, though, by entrepreneurs. For 40 years, from 1975 to 2015, okay, this could do 140 tons to Earth orbit. But from 1975 to 2015, the strongest launch vehicles in the world could only do 20 tons to Earth orbit. Okay, and there was no reduction in space launch cost either. No increase in capability, no reduction in cost over a 4-decade period. But now this has changed dramatically. Okay, SpaceX just introduced Falcon Heavy, which can do 60 tons to Earth orbit and is 3/4 reusable and costs a factor of 5 less than other launch vehicles in terms of cost to orbit. And they are in the process of developing a heavy lift vehicle called the Starship, which will be 100% reusable and have a capability of 150 tons to orbit, actually slightly more than the Saturn V, but be reusable. And with a vehicle of that character, or this character, frankly, but that would be cheaper, and given that a half century has gone by, it would be nice if we actually advanced on this, would have the capability of sending the required payloads to Mars. Okay, now, but whatever the launch vehicle is, okay, it can send 120 tons or more to Earth orbit. It can send 40 tons on trans-Mars injection. And that's how we're going to do the mission. Lift and throw and let it go. We're not going to be sailing spaceships around the universe. Okay, we're just going to send payloads to Mars, except they're bigger than the payloads we've been sent in our unmanned program. Now, the first payload we sent to Mars is an unmanned spacecraft. Okay, it goes to Mars on an 8-month trajectory, a minimum energy trajectory. Am I speaking too fast? Because obviously you speak English as a second language. And, is it okay? Okay, va bene? Okay, all right. It takes 8 months, and then it deploys an aero shield. It uses that to make friction against the Martian atmosphere, and is captured into Mars orbit. And then, after we check out the weather to make sure that things are good, we bring it into the atmosphere in a more substantial way and slows it down to subsonic speeds. And then we pop a parachute and we come down slow and we put ourselves down softly on the surface with rockets, just like InSight did last year. And now we have a payload on Mars. Now, what is the payload? It consists of a number of things. The primary object is this is a small rocket vehicle. Well, it's large compared to what we've sent to Mars so far, but it is a craft for sending a crew of 4 from Mars to Earth in the final stage of the mission. Okay. 6-month transit. So it's got a small cabin here, 5 meters in diameter, 6 meters tall, so 2 decks each with 3 meters of ceiling. And then it has 2 methane oxygen chemical propulsion stages, which are unfueled. They have to be unfueled, or this would weigh 4 times as much as it does and be much too heavy for a vehicle of the Saturn V class to send to Mars. And then in the original design of this mission, which I'll talk, is we do bring some hydrogen with us to Mars. We have about 6 tons of hydrogen here in the lower stage tanks that are later going to contain methane. Now, recently, the radar, in fact, Italian radar on the Mars Reconnaissance Orbiter discovered large glaciers on Mars in the northern hemisphere, going as far south as 38 degrees north, which is the same latitude as Athens on Earth. So this is not just in the polar region, it is way down here in the sunny Mediterranean. Not sunny today, but sometimes. And they're covered by, a meter of dust. That's why they're not visible by telescopes, but they're essentially at the surface. They're within a shovel distance of the surface. And they could provide the water and so that you wouldn't have to bring hydrogen to Mars. Okay? But and then slung below this vehicle, not shown in this diagram, we have a light truck, like a small pickup truck. It runs on a methane oxygen engine, And in the back of the truck, we have a nuclear reactor with a power of about 100 kilowatts. Okay? Now, after landing, the truck is telerobotically driven a few hundred meters away, unwinding a cable off the back as it goes. And then the reactor is lowered to the ground, preferably in a depression in the terrain. Small crater, a ditch, the reverse side of a hill, anything to put a substantial amount of dirt between the reactor and the lander for shielding. And then we turn the reactor on, and now we have power, okay? And what we can do, I'll just talk this as if we're bringing the hydrogen. If you're using water, it's quite similar. You react hydrogen that you brought or that you made out of water with carbon dioxide. In the presence of a catalyst, it will produce methane and water. The methane is fuel. It's excellent rocket fuel. We store that in our tank. And of course, the methane is the fuel that has now been chosen for New Glenn, for Starship, for Vulcan. There are methane engines of various sizes being produced right now. And they give you the second highest specific impulse of any chemical engine right after hydrogen oxygen, but much more storable than hydrogen and oxygen and much more compact. So there's your methane. You take water, whether you got it from Mars or whether you got it from this reaction, and you split it into hydrogen and oxygen. The oxygen is your oxidizer, and the hydrogen is recycled to make more methane. And then if you're actually using Martian water, you do have enough oxygen combined with the methane. If you're using hydrogen from Earth, you need extra oxygen, which you could get by splitting carbon dioxide into carbon monoxide and oxygen. The oxygen is extra oxidizer. The carbon monoxide can be released as waste. There is no environmental protection agency on Mars. So that's probably what we'll do on initial missions. Once we have Martian bases, though, there's a use for the carbon monoxide. We'll use it to make steel because the Martian ground is largely iron oxide, and the way you make steel on Earth is by reacting carbon monoxide with iron oxide. That's how it's done. And in fact, at my company, Pioneer Astronautics, we recently completed a little project for NASA demonstrating this, but it was pretty well established that you could do it. So when you're all done, you're producing 108 tons of methane oxygen bipropellant on Mars. And whether you have to bring the hydrogen, it's 6 tons of hydrogen. If you're using Martian water, you don't need to bring any hydrogen, but you have to bring some extra robotic equipment to mine the water. Okay. But either way, you've produced a lot of propellant, an awful lot of propellant, representing something like 20 times the mass of the equipment required and consumables required to create it. So it's a very high leverage, and because of that, we produce more propellant than the Earth return vehicle needs. The Earth return vehicle in this scenario only needs 96 tons of propellant. We have 108. The extra 12 tons is used to power ground vehicles that run on methane oxygen engines. They give you great field mobility, much better than you can get with electric vehicles running on batteries, and this is what you need. We're going to Mars to explore. The number one requirement for exploration is mobility. It also gives you a mobile source of power, so that if you need high power at a distance from the base, say for drilling, you have it. And this is also important. You see, what I'm saying is that the ability to make use of local materials, the ability to turn local materials into resources, is the key not only to making the mission cheap, but making it effective, which is equally important, because there's no point going to Mars unless you can do something useful when you get there. Okay? So there you go. We've built machines that do this chemical synthesis. This one you're seeing here is actually full scale. not for the human Mars mission, but for a Mars sample return mission. And it works, which is not surprising because this is just 19th century industrial chemistry, although automated using 20th century electronics. So, it took 8 months to fly to Mars. It took 10 months to make the required propellant, given 100 kilowatts. And there's 26 months in between launch windows from Earth to Mars. So, well before the next launch window has opened up, we will know we have a fully fueled Earth return vehicle waiting for us on the Martian surface. That being the case at the next launch window, okay, which could be, in my view, in the late 2020s or early 2030s, if we were to take this seriously, we launch 2 more payloads to Mars. One sends out another Earth return vehicle system. The other sends out a crew with an habitat spacecraft with 4 astronauts in it. Okay, now, why 4? Because the mission will scale with the size of the crew, so you don't want a very big crew if you really want to do this. And 4 is the smallest number you can have where you can divide it up into 2 parties and have no one be alone. That's why I prefer 4. It's enough. Okay, now because our ride is waiting for us on Mars, we don't need to fly to Mars in, a giant, electric propulsion spacecraft, obviously modeled on the Imperial Star Destroyer. We don't even need to fly to Mars in a comparatively modest Millennium Falcon. Okay, we can fly to Mars in a tuna can. And this is fortunate. Tuna cans have proven heritage for packaging. Now, of course, this is somewhat larger than the one you use to buy tuna. It is 8 meters in diameter, and the useful section is 6 meters tall. So it's 2 decks, each 3 meters high. The upper deck is the actual living quarters. The lower deck is more of a garage, workshop, cargo hold kind of place. This is a diagram of one potential layout of the upper deck of the HAB. What you see here is a central area, and I'll talk about that in a minute, around which there's 4 staterooms. Here's the bathroom, science area, exercise area, wardroom, galley, lounge, and the central area is the solar flare storm shelter. Okay, it's worthy of comment. There's 2 kinds of radiation hazards in interplanetary space. There's solar flares, cosmic rays. They're different. Solar flares come from the sun. They are irregular events. You might have a large one about once a year, okay, in which a sievert, well, more than a sievert, you might have 10 sieverts or 20 sieverts of radiation, which is delivered in the course of a few hours, which is enough to kill either immediately or after a brief period of radiation sickness. That is the bad news. And you might have one such event about once a year. You might have more or less. It's a matter of chance. But we could expect to experience one in the course of a human mission to Mars because we're going to be traveling 6 months out and 6 months back. So unlike a lunar mission in which you don't need to deal with this, you can just trust to luck that it's not going to happen during a 3-day trip one way to the moon. It probably will happen on the way to Mars. But the good news is that the kind of radiation that it is protons with energies of about 1 million volts. Okay? And they can be stopped by 12 centimeters of water, or things that from the nuclear point of view are essentially the same thing as water, such as food, or things that water and food become as the mission develops. And we have enough of that on board the ship to pack it in around the central area, and we create basically a pantry storm shelter. So solar flare happens, the alarm bell rings, everyone goes in here, and we're packed pretty tight for a few hours until the all clear rings and you come out and you're safe. And that's how you are safe against the solar flare. Now the other kind of radiation is entirely different, is cosmic rays. Now cosmic rays do not come from the sun. In fact, we don't really understand where they do come from or how they could come from anywhere, because they are particles with energies not of millions of volts, but of billions of volts. 1,000 times more energy, particle for particle, than solar flare particles. So we don't understand their origin because they cannot be created by nuclear reactions, which only have reaction energies on the order of 1,000,000 volts. Okay? So the process that gives rise to them is unexplained. However, there's no question that they do exist. They come into our solar system from interstellar space. And you can't stop them with 12 centimeters of water. They'll shoot right through it. So the bad news is you're going to take the dose. Okay? You don't have meters of water needed to stop them. Okay? The good news is that the magnitude of the dose is not that big. It's only around half a sievert per year for every year you're in interplanetary space. So we could expect the crew to get half a sievert during the transit, half of that going out, half of that coming back. We won't get much on Mars. On Mars we have shielding available to us. And Mars underneath us blocks out half of the sky. We can put sandbags on the roof of the HAB. Martian atmosphere itself does block some of them. So we'll get half a sievert. What's half a sievert? What does that represent? That represents no immediate hazard. Okay, that is unlike 10 sieverts where you see a result. Half a sievert is more of a statistical risk, like smoking, where there is no immediate effect. There is a statistical increase in your chance of getting cancer. Okay, now half a sievert, about a 1% extra risk that you will die of cancer at some time later in your life. Now, let's put that in context. I don't know the statistics for Italy, but in the United States, it's probably not that different. Okay, the average American, if you do not smoke, you have a 20% chance that you would die of cancer. This would make it 21. For the average American smoker, it's 40. So, in fact, if we recruited the crew out of smokers and sent them to Mars without their cigarettes, we would be reducing their chance of getting cancer. So, one reason, therefore, to send people to Mars would be for their health. Okay, and I should point out that we have proof of this, not just from general radiation health knowledge, but from specific individuals. There are now over 10 astronauts and cosmonauts who have spent enough time on the space station where they have gotten cosmic ray doses comparable to going to Mars and back. And we have seen no radiological casualties among this group. Okay, now, you wouldn't expect to. If you have a statistical risk of 1% and you have 10 people that have taken that chance, chances are no one has been hit. And in fact, none have. Okay? So this is an element of risk, but it is actually a small part of overall mission risk. So I would say that provided you provide a solar flare storm shelter, which you need to do, the radiation risk of Mars mission is a small part of mission risk. It is not a showstopper on the way to Mars. Okay. Now, there is another health hazard in space, which actually we have experienced and seen quite directly. And it's not radiation. Radiation gets all the headlines because it's something that is scary. But actually, the thing that causes the visible health effects in space is not radiation, it's zero gravity. Okay? Zero gravity deconditioning of crew. When you're in zero gravity, you don't get the workout that you get every day on Earth. I mean, just walking around here, I mean, I'm not an athlete, but I do walk around, and here I'm carrying, you know, whatever, 75 kilograms I'm carrying around wherever I go. So I'm getting a certain amount of exercise just by functioning on Earth. You don't get that in space. And so bones and muscles deteriorate. And astronauts who spend 6 months on the space station, unless they very religiously follow the exercise program of 3 hours of exercises a day, come back severely deconditioned and in many cases have to be carried off of the capsule, although they do recover functioning within a couple of weeks on Earth. So while this is not life-threatening, this definitely does impair functionality. And we're going to Mars to explore. Field exploration on Mars will require hiking around wearing a big bulky spacesuit. True, its weight is reduced by the lower gravity, but still this is a physical activity. We do not want the crew deconditioned. And therefore, I strongly recommend that we go to Mars with artificial gravity. Now, this is the upper stage of the booster that threw the payload to Mars. So it's going to Mars too. We can use it as a counterweight on the end of a tether. This tether is about 1.5 kilometers long. You spin this at 1 revolution per minute, you create Mars gravity in the habitat. You spin it at a little less than 2 revolutions per minute, you create Earth gravity in the habitat. And this is how we avoid the deconditioning effects of zero gravity. You make a lot of other things easier too. Okay, you make it possible, for example, to cook on Mars in the spacecraft in the same way as you do on Earth, because everything doesn't have to be enclosed because of zero gravity. You can actually fry an egg. Okay, you can do all sorts of things without the inconveniences. But the primary necessity is to avoid zero gravity deconditioning. Now, I believe that we should start doing artificial gravity experiments in space. It is a remarkable thing that we have been sending spacecraft into orbit since 1957, and there has only been one artificial gravity experiment ever done, which was done by the Soviets in 1977. They sent a couple of rats up in a rotating spacecraft where they subjected them to 1 gravity. And they were actually there as a control against other rats who were in zero gravity. Okay. I believe that it would not be terribly expensive to have a small spacecraft, say 1 meter in diameter, you spin it at 25 RPM, you create Mars gravity in the perimeter, you create lunar gravity halfway out. Okay, you could put mice in it, and we could see how mammals on Earth respond to artificial gravity for long periods of time, respond to Mars gravity for long periods of time, lunar gravity. We could see how their children born and raised in partial gravity develop, which is something of interest for the human future in space. Will children born on Mars develop properly? Okay, we could start this immediately. I believe this could be a very low-cost mission. I believe it's entirely within the means of the Italian Space Agency to do something like this. In any case, they're flying to Mars on a 6-month trajectory. Why a 6-month trajectory? The minimum energy trajectory to Mars is 8 months. But it turns out that with a little extra propellant, you can get there in 6. You don't lose that much payload. in going there in 6. And in fact, Insight last year got there in 6, as did Spirit and Opportunity in 2003. Okay? So 6-month trajectory to Mars are possible, and it's nice to speed things up a bit and without significant loss of payload. Now, if you try to get there in 4 months, you start going up in exponential. It takes a lot more propellant and your payload goes down substantially. And in fact, in my view, it becomes a negative trade where you're losing capability, you're losing redundant life support systems and things like this for the purpose of shortening the transit, and you're actually making the mission less safe. Okay, so that's why you would want to take about 6 months. But why exactly 6 months? Why not 5.9 or 6.2? Okay, well, the reason why 6 months is the answer, okay, is because the 6-month trajectory to Mars is also the free return trajectory. That is, if you decide to abort the mission and not go to Mars, if you're on that trajectory, you loop out to about 2 astronomical units away from the sun, and then you loop back, and you'll go to 1 astronomical unit away from the sun, and you will get there exactly 2 years after you left, which means that the Earth will be there too. Okay, so you'll come back at exactly the right time to meet the Earth and return home. If you try to go to Mars faster and you abort the mission, you'll fly out further than 2 AU, and you'll come back after 2 years, and you'll have missed the Earth. If you fly to Mars slower, you'll come back sooner. Okay, slower, sooner, okay, faster, slower. And once again, you'll miss the Earth. So this is the right trajectory for a human mission to Mars. If I had a superior propulsion system, say nuclear thermal rockets, I would not use it to go to Mars faster. I would simply use it to increase the payload, staying on the 6-month trajectory. That's what I would do. Okay, but in any case, they're on a 6-month trajectory to Mars. When they get close to Mars, they fire a pyrotechnic that cuts this cable. This thing goes away into interplanetary space. They aerobrake into Mars orbit, and then after we assure ourselves the weather is all right, we go and we land at landing site number 1, where the fully fueled Earth return vehicle is waiting for us. Now, we've had equipment on the ground at landing site number 1 for 2 years. We have thoroughly explored the area with robotic rovers that have identified all landing hazards. They have placed a beacon, a radar beacon, on the ground that the pilot, of course we have a very good pilot, best in the world, can fly to. We should be able to land right on the spot. But let's say we don't. Let's say somehow the landing is off by 10 kilometers, 20 kilometers, 50 kilometers, 100 kilometers. We're still okay, because we have with us in the lower deck of the Ham a pressurized ground roving vehicle. Is like a small sport utility vehicle. Runs on a methane oxygen engine, has a one-way range of 1,000 kilometers. 1,000 kilometers one way. So it would really take incredibly bad piloting to land outside of that radius of action. But let's say that happens. Let's say instead of landing here or even here, they land over there on the wrong side of the planet. Okay. This would represent a very serious problem with the pilot selection process. Now, if that happened, if you land over here, you can still save the mission because you have the second Earth return vehicle following you to Mars, and if that happened, you bring it down to land over here. Now, in that case, you would be depending upon the chemical synthesis to work in real time instead of previous time. But the success of the technology has already been proven by the first lander, and we do have a human crew on the scene to adjust the equipment should it malfunction when they are there. Though, of course, in this example, you would not want the pilot to participate in that activity. But you do have 3 sane crew members, and they can do it. Now, And in any case, this is a third level mission backup. Now, finally, as a fourth level backup, if you cannot land accurately, if you can't drive there, if you can't use the second Earth return vehicle, there's a fourth backup, which is that we have the whole crew landed on Mars, where we have natural gravity and substantial radiation protection offered by the Martian environment, and we have enough supplies to last for 3 years. So if worse comes to worse, we can just endure on the surface of Mars, get a lot of exploration done, and wait till the next launch window opens up 2 years later, which will send out more supplies, reinforcements, and another return vehicle that will take us home. So we have an abort option and a 4-layer defense in depth on carrying out the mission itself. Okay. But let's say things work out as they should. Okay, we land at the primary site. We already had automated health checkout on this vehicle, but now we can inspect it directly. It is fine. We do not need the second Earth return vehicle. We land it somewhere else, where it will start making propellant along with that will be used to support the next human mission, which will fly there 2 years after that, along with another Earth return vehicle, which is their backup, but which otherwise opens up the third landing site. And I think if we're smart, we'll land this not anywhere very far away, but a few hundred kilometers away. It will define a new place to explore, but it will be within at least one-way driving range from the first landing site. So the crew will have available to them 2 complete Earth return vehicles, either one of which can take them home. So we're very heavily backed up here. So, the 2 boosters every 2 years. That's an average of 1 per year. When we were launching space shuttles in a serious way, we had 6 a year. Okay, SpaceX is currently launching Falcon 9s at a rate of twice a month. Okay, so if they can launch Starships even 6 times a year, and knowing them, it'll be more than that, we'd only be using a small fraction of our heavy lift capability to support this program. Which means we can do the moon in parallel, we can do asteroids in parallel, we can do large-scale space observatories in parallel. It's not like we have to sacrifice the whole space program in order to do this. We can do this as a measured part of a comprehensive and extremely rich space exploration program. So this is an actual photograph of the Mars base. Well, not exactly. Okay. This is a painting, and so here's the Earth return vehicle. Upper deck there's the habitat, the 2 chemical propulsion stages, the synthesis equipment, the reactor and the crater in the background. Here's the tuna can hab. Upper deck for living quarters, lower deck is the garage for the little exploration vehicle. Some solar panels that provide backup power if we have to turn the reactor off. Hard to see, but this is the light truck that was used to deploy the reactor. That's a backup vehicle for this one. We have actually 4 sources of power available to the base: the reactor, the panels, and the engines of the 2 vehicles. This is an inflatable greenhouse. This is an experiment. It's not mission critical, but it's an experiment for the future in learning how to grow crops on Mars, in Martian water, Martian soil, Martian gravity, Martian sunlight, for the benefit of future missions and future bases. Now, we're going to be on Mars for 1.5 years. Why 1.5 years? Because if you're taking 6-month transits to Mars and 6 months back, 1.5 years is how long you will have to wait for the planets to move around to give you your launch window back to Earth. But if you think about it, if you're spending 2.5 years in space, you want the majority of that time to be on Mars. There is an alternative flight plan, which is known as the opposition plan, which is a 2-year round trip, but it only spends 1 month at Mars. So that plan spends 5% of the mission on Mars. This plan spends 60% of the mission on Mars. That's the productive part of the mission. That's what the mission is about. and therefore I believe this is what's known as the conjunction class mission is the right plan. It also, by the way, has lower propulsion requirements. So it's not only more productive, it's also cheaper. So you're going to be on Mars a year and a half. And you're going to explore. Now, what are you exploring for? There's all kinds of things people want to know about Mars, the geology, the mineralogy, the aeronomy, the weather. But there's two fundamental sets of questions about Mars that make it of interest to humanity at large. The first set of questions revolve around the issues of was there or is there life on Mars? Now, this is a real photograph of Mars. This was taken by the Viking orbiter in 1976. And what you can see here are dry riverbeds on Mars. Okay, there are no canals on Mars, okay, but there are dry riverbeds on Mars, thousands of them, and dry lakes, and even the basin of a dried up ocean. And the evidence is that there was liquid water on the surface of Mars for about 1 billion years, which is 5 times as long as it took life to appear on Earth after there was liquid water here. That is, within 200 million years of when the Earth had cooled enough for there to be liquid water, we find fossils of bacteria on Earth. Okay. And they may precede that. Those are just the ones that we found. Okay. So life appears on Earth very quickly after there's liquid water. There's liquid water on Mars 5 times as long as that duration. So if the theory is correct that life develops from chemistry through chemical complexification wherever it has appropriate conditions, then it should have appeared on Mars. And if we can go to Mars and find fossils of past life on the surface of Mars, we will have proven that the development of life from chemistry is a general phenomenon in the universe. See, we now know from the Kepler Space Telescope that planets are a general phenomenon, that most stars have planets. Furthermore, actually the conclusion of the Kepler team is that 1 in 5 stars has an Earth-sized planet in the habitable zone. Every star has a habitable zone when you have the right temperature for liquid water, near or far, depending on the brightness of the star. 1 in 5. 100 billion such planets in the Milky Way galaxy alone. And we also know the development of life after its origin is a causal phenomenon. That is, it is a continuous development of greater complexity, greater capability for activity and intelligence, and in fact ever more accelerated evolution, okay, has been an ongoing phenomenon in life on Earth. So if life develops everywhere, it means complex life, intelligence, civilizations probably develop almost everywhere. It means we're not alone. This is really worth finding out. Now, water erosion features all over the place visible on the surface. Liquid water detected, once again, by the Italian ground-penetrating radar on Mars Express. That is a place where life could exist today. And in fact, there's every reason to believe that the liquid water underground on Mars is not limited to that one location, but it's probably in lots of places, that there's a Martian water table. Which is a very interesting thing. We want to know about that water table, because if we can drill down into that water table, we would be able to find, if it exists, extant life, that is survivors, living microbes on Mars. And because, I mean, I think it's a very good reason to believe that if there was ever life on the Martian surface, when surface conditions deteriorated, they would have retreated with the liquid water into the underground, just as they have on Earth. That is, the first life on Earth were anaerobic microbes which could not tolerate oxygen. Okay, green plants put oxygen in the Earth's atmosphere. It was not there at the beginning. Life has radically transformed the Earth's environment. And the original inhabitants, for them, oxygen was toxic pollution. And so they had to retreat into the underground 3 billion years ago. They're still there today. They're still there today. They have seen everything above them come and go. They have seen the trilobites come and go. They have seen the dinosaurs come and go. They've seen the mastodons come and go. They've seen the Wehrmacht come and go. Okay, you know, and they'll be there after we're all gone. Okay, so if there was ever life on Mars, it's there in the underground, and we really want to have a look at it because we can find out something really fundamental about life, which is what it is. See, all Earth life is the same at the biochemical level, whether you're talking bacteria, mushrooms, crocodiles, or people. We all use the same genetic code. We all use RNA and DNA with the exact same set of amino acids. We all use the same alphabet. Okay, now, here am I speak English. We use the Latin alphabet, as do you, okay? Although in Italian, a number of the letters are pronounced differently than we do in English. I don't know why you got that wrong, but however, okay, this is not the only alphabet in the world. There's the Russian alphabet. Now that is actually different than our alphabet, although it is related. A number of the letters are the same. There are some letters that are different. Some of the letters that are the same are pronounced differently, but it uses the same principles of turning letters into sound. It's a similar system, and it does share a common origin, okay, which is both the Latin alphabet and the Russian alphabet originate in the Greek alphabet, okay. Now, then there's the Hebrew alphabet, which is even more different, but in fact it has a common origin with the Greek alphabet in the Phoenician alphabet, okay. But the Chinese alphabet is completely different. It doesn't share a common origin at all. It doesn't share the same principles of operation of turning letters into sound in any way whatsoever. And the Chinese language operates on completely different principles than Western languages do. Okay, where tone can change the meaning of a word and so forth. It's just a completely different information system. No common origin. Okay, although I would imagine that linguists can look into it and see certain psychological relationships that underlie language that are the same. But if you simply stick with language and letters themselves, it's totally different. Okay, so the question is this: does all life in the universe use the Latin alphabet? Or are we just one example drawn from a much vaster tapestry of possibilities? There's reason to believe that all life uses carbon and water as its chemical basis, but DNA, RNA, and those specific amino acids, that's idiosyncratic. Okay, so this is something really fundamental. So we want to search for underground life on Mars. Once again, ground penetrating radar is the way to explore underground. And I mean, look, most of Mars is underground. Most of the Earth is underground. It's like most of the ocean is under the surface. And okay, we've done some with the satellites. These are mostly in long wavelength radar because it can go very deep. The bigger the wavelength, the deeper you can go, but the less precision you have in knowing what you're seeing. Okay, I'd like to send spacecraft to Mars with ground penetrating radar, not 10 meter and 20 meter frequencies, but 1 meter of frequency, 2 meter frequency, half meter frequency. In that range, because that will get you down 20 meters, 40 meters. I'm interested in the first 50 meters of Mars, because that's the part that Mars that we can reach. I'm interested in looking for water. I'm interested in looking for caverns, lava tubes, all sorts of phenomena like this, places where life could exist. And in the case of caverns and lava tubes, places that might be very attractive to put a permanent Mars colony. Okay, and these could be put on satellites, although I'm very interested in doing something a little different, because we're stuck with satellites and rovers crawl and satellites go zipping around. I like balloons. Okay, there are a kind of balloons known as super pressure balloons that they're strong enough that they don't have to vent gas in the daytime, which means they don't have to drop ballast at night, which means they can cruise for months without ever coming down. The world's record duration flight on Earth is 700 days for a super pressure balloon. Imagine releasing a bunch of super pressure balloons with small gondolas carrying 1 meter ground penetrating radar on Mars. They cruise all over the planet, Martian winds taking them at speeds of 60 kilometers an hour all over the planet. The winds of Mars are its highways, and they would cruise all over the place, and radar works much better if you're closer. Instead of being at 300 kilometers up, you'd be 3 kilometers up above the ground. You'd also be taking photographs from there, both for the photographic science, but also to provide context imagery for the radar itself. And also, by being so close to the ground and traveling at moderate speeds, you'd know exactly where you are. And we could find features that would be very interesting to explore and exploit, and be a great global exploration mission. And the technology was there, and it would not be terribly expensive. And I think you should do it. Okay. But that's just me. Anyway, we're going to be on Mars for a year and a half, okay, exploring, trying to find the evidence of past life, trying to find places where we could sample current life. At the end of a year and a half, we get in the Earth return vehicle, we start, I want to talk about something else. Okay, we're exploring on Mars. We have 4 people there, okay, and probably 2 are qualified field scientists and 2 are really flight engineers whose primary responsibility is to keep all the systems working. That's really the 2 primary skills needed on the mission. Okay. I'd like to have 1 million people alongside. How do we do that? We send ghosts. Very lightweight ghosts. How do you do that? That's the virtual reality. Okay. Now, okay, Antonio mentioned we have a Mars station. This is actually our Mars station in the Arctic, which was the first one we built. This is on the rim of a large meteor crater on Devon Island, 75 degrees north. We built another station like this one in Utah, southern Utah. It's in a desert there. And we actually have a crew in it right now, and we have crews in it about 8 months a year, and it's much more accessible and cheaper to operate than the one in the Arctic, although the terrain here is more specifically Mars-like. But the one in the desert is very interesting because, okay, it's in an area of sedimentary rocks which are fossiliferous, and our crews operating in SIM have actually made significant paleontological discoveries there. We discovered a dinosaur fossil find there, which is the largest dinosaur fossil find in North America in 30 years. Okay, but here's the idea. This is what I'd love to do. Okay. Well, let me explain how we're going to do this on Mars, and then how we'll do this in Utah. Okay. The crew on Mars, in their initial explorations, go out on fast-moving rovers with high-definition cameras, filming everything all over the place. Okay. and we create a huge amount of data which we transmit back to Earth, and we create a virtual reality simulation of the territory on Mars. Okay? We can film it faster than we can study it. We create the virtual reality terrain, okay, with fast reconnaissance. Then we go out to actually study it, but now people on Earth can put on the virtual reality gear and go walking around this terrain and start studying it, and they say, hey, this rock over here, this is anomalous. Could this be a fossil? Hey, come over here, look at this, hit this with a hammer. And be directly collaborating with the crew on Mars. And this is a way, if you wish, it's a way to democratize Mars exploration by having thousands or millions of people on Earth directly participating alongside the astronauts. Okay, but it's a way to greatly amplify the amount of work that gets done. NASA is already doing this in a small way with the Mars Reconnaissance Orbiter, which takes high-definition photos from orbit and takes them much faster than the professionals can examine them. They've put them out to amateurs to examine, and numbers of amateurs examining these photographs have made significant discoveries. Okay, but imagine now a dynamic collaboration between astronauts or rovers on Mars and virtual astronauts from Earth. So, how do we demonstrate this? I think we can demonstrate this technique now at the Mars Desert Research Station. That is, we could send teams there to film the whole territory around the station in high definition, create a virtual reality simulacrum of that environment. Now, it's not a make-believe virtual reality created by artists, but a real virtual reality of that terrain, and have people here in Italy be exploring alongside crew members in the desert in Utah, and demonstrate this new kind of collaboration between virtual explorers on Earth and those in the desert in Utah and ultimately on Mars. And that this is a new kind of exploration technique that we can pioneer together. Anyway, we're going to be on Mars for 1.5 years doing this. The 4 astronauts that are there and the 4 million ghosts exploring alongside them. I call them ghosts because they're like the protagonist in the movie Ghost, Patrick Swayze. He could walk around, he could see everything that's going on. It's just he couldn't actually push anything. Okay? Except that now we'll have the astronauts playing Whoopi Goldberg. The ghost wants you to do this. Okay. Anyway, so we're doing this for 1.5 years on Mars. Okay. At the end of that time, we get in the Earth return vehicle, we start it up, and we take off and we go back to Earth. We leave all the rest of this stuff behind on Mars: the habitat, the reactor, the vehicles, the solar panels, greenhouse. Is that bad, leaving all this really expensive aerospace hardware behind on Mars? Wouldn't we like to get it back? No, we don't need to get the stuff back. We have a lot of stuff here already. What we need to do on Mars missions is bring as much stuff to Mars as we can and come back with as little as we can, because everything we take to Mars is available for future missions to use. So, like, here is a map of Mars, and here's a nominal landing pattern. The landing sort of the centers of these circles. Texas is here for scale, okay, and Texas is about the same size as Italy, so that gives you a sense. This is like Italy, and you can see Mars is a lot bigger than Texas, okay, but each one of these landings, okay, the radius of these circles are 500 kilometers. I mentioned our vehicle has a one-way range of 1,000 kilometers, so you can go out 500, come back 500. You could explore a territory of about this size, about the size of a major Western European nation each mission could explore. The centers are separated by 800 kilometers, so you could drive from Italy over to France or something. But in any case, after a number of these missions have occurred, we'll have opened up a territory on Mars for exploration about the size of Western Europe. And after that exploration has occurred, we'll know the answers to these questions. Is there life on Mars? Or we'll have confidence in a negative answer if there never was life on Mars. And after that, the key question about Mars is going to change to the second set of questions, which is not, was there life on Mars? It's, will there be life on Mars? Because the key issue, which is even more important about Mars, is that Mars is more than an object of scientific inquiry. It's a world. It's a planet with a surface area equal to all the continents of the Earth put together, and has on it all the materials needed to support life, and therefore potentially technological civilization. And if you can go to Mars and establish a base on Mars for the purpose of learning how to take Martian materials and turning them into resources, we can make Mars habitable. Now, what do I mean by turning materials into resources? Aren't there natural resources? No, there's no such thing as a natural resource. There's only natural materials. It's human creativity that turns materials into resources. Land was not a resource on Earth until people invented agriculture. Oil was not a resource on Earth until we developed oil drilling, refining, and machines that could use the product. Uranium was not a resource until we developed nuclear power. Deuterium is not a resource now. It will be once we develop fusion power. Okay? It is the relationship between the material and your mind that defines whether it is or is not a resource. It is people that are resourceful. Okay? We establish a base. If we can learn how to use these materials, turning them into resources, okay, make Mars habitable. Now, what do I mean by make Mars habitable? Do I mean terraform the planet? You know, like in Star Trek II, The Wrath of Khan, where they take the Genesis planet and they turn it from a lifeless desert into a fully living new Earth covered with forests and jungles and coral reefs and birds and butterflies and chipmunks and flying fish. Yes. That is what I mean. And I have faith that we will do that with Mars someday. And the reason why I believe that is because we're life. And it is the nature of life to take barren environments and transform them into places that are friendly for the development and propagation of life. Okay? That is why life on Earth has been a success. Life has transformed the Earth. Life does not leave things sterile. It makes them fertile. And life put oxygen in the Earth's atmosphere. Life turned the dirt into soil on the continents. And symbiotic communities of plants and animals advancing from the ocean up the seashores, up the plains, up the hills, and up the mountains, as high up as life can go, it goes. And no sooner does any sterile place appear on Earth than life transforms it. Think of Hawaii coming out of the Pacific Ocean, this huge piece of sterile basalt. Microbes come and they create soil. Birds come and they drop seeds so the place becomes lush. Polynesians come and they let loose pigs so there's something good to eat. Okay, Europeans come and build swank hotels so there's a nice place to check in. This is what we do. It's what we do. Okay? And it would be unnatural if humanity, as the kind of bird, as it were, that the biosphere has evolved, capable of transporting the seeds of life from this living planet to currently barren planets on the other side of the ocean of space, did not do that. So we're going to do it, okay, someday. But that is not what we are going to do. We who are in this room, we who are working in the space program right now. Nevertheless, we can have the honor of transforming Mars in a different sense. Not so much physically as intellectually. Because, as I said, the thing that determines whether an environment is habitable or not is only partially a function of the material nature of the environment. It's also a function of the intellectual apparatus you bring to it. Okay? Two people can be stranded in a forest. One could starve to death in 3 weeks. The other could live there forever in comfort. And the difference is to one, the ability to turn the materials of the forest into resources is unknown, and to the other they are known, and therefore the resources are visible all around him or her. Okay. And so we establish a base for the purpose of doing exactly this. Okay. We go beyond the Mars Direct, which is the beginning of learning how to use water and carbon dioxide to make fuel and oxygen. We learn how to grow food on Mars. We learn how to extract geothermally heated water from the subsurface, give us power too. We learn how to make bricks and ceramics and glasses and plastics and metals and wires and tubes and habitation structures. We move up this progression of craft to the point where human beings can become self-sustaining on Mars, and so that new branches of human civilization can grow on Mars, which in the fullness of time will grow in size and population and industrial capacity and technological know-how to the point where they can actually address the question of transforming Mars itself. And so we don't just bring life to Mars, we bring Mars to life. That's the program. Okay? And that's just the beginning of the program. Because Mars is not the destination, it's the direction. Okay? You know, Christopher Columbus crossed the Atlantic in ships that even 50 years later no one would have attempted to cross the Atlantic in. No one. Because there weren't Atlantic-capable ships in Columbus's time, because there was not transatlantic Western civilization in Columbus's time. But once European civilization became transatlantic, the better ships followed. So 50 years later you have three-masted caravels, and soon after that you have clipper ships, and then steamboats, and ocean liners, and Boeing 747s. And now what was once a heroic passage is a matter of luxury travel. Watching movies for a few hours. And similarly, once human civilizations are established on Mars, this will drive the advance of space propulsion. Okay, the first people that go to Mars will go in tuna cans, spacecraft like this taking 6 months. Okay, their grandchildren, when they travel back and forth between Earth and Mars, will do it on fusion-powered spacecraft that do the trip in a week and a half. And they'll wonder at the stories of their immigrant parents or grandparents who came over under much harsher conditions. Just as we Americans sometimes, when we hear the stories of our grandparents who came over in the early part of this century or in the last century, wonder at how they did. But they will do it. And the same sort of advanced propulsion ships that make it a matter of routine to travel around the inner solar system will make it possible to colonize the outer solar system and ultimately the stars. So that's what we're doing. And you know, about 20 years ago, there were a bunch of books published with titles like The End of History, The End of Science. Everything significant has already been done. Everything significant has already been discovered. You know, it's been an interesting thing. You can read about it in your books, but it's done. Sorry you missed it. Well, it's been clear since then. There's been a lot of discoveries, including on Mars and Kepler and Hubble and all this. But it's not even that they were wrong. They were just totally backwards. I think that if we do what we can do in our time, which is establish this first human foothold on the first new world, then 500 years from now, there will be new branches of human civilization, with their own literatures, their own dialects, their own histories of epidemics, their own ideas on social organization, their own massive contributions to science and invention, discovery. Okay, there'll be such civilizations not only on Mars, but on thousands of planets orbiting stars in this region of the galaxy. And when they look back at this time, they're not going to think of this as the end of history. They're going to think of this as the beginning of history. Okay? So we today, we are literally present at the creation. And those of us who are operating in the space program or are studying to become operating in the space program are tremendously privileged. We have an opportunity to be among the creators. So this is a truly grand time. And thank you for being part of it. I'd be delighted to take questions. Someone's got to have a question. Want to know where I got the time? No, the,
So,
sir,
have you established a cost of your program, and have you identified a roadblock that haven't made it possible? Do you think that SpaceX and Blue Origin are going to hold on and execute better launchers than SLS?
that's not hard. Okay, well, okay, when I first designed the Mars Direct plan, I designed it for NASA, and in contrast with the 400 billion plan that they had come up with, known as the 90-day report, which involved building everything conceivable before you went to Mars, moon bases, orbiting spaceports, all this stuff. We had costed this thing at about $30 billion. Mike Griffin, who was then associate administrator for NASA exploration, then said to NASA, you need to take a look at this. So NASA Johnson Space Center took Mars Direct and they designed their own version of it. And it was larger. They had a crew of 6. They had larger spacecraft. They had more equipment of every kind. Okay, and they costed it out at $55 billion. And I said, well, it doesn't have to be 55. It can be 30. You don't need this. You don't need that. And Carl Sagan, who was here, Bob, listen, it doesn't matter. Okay, it doesn't matter whether it's 30 billion or 50 billion. It matters that it's tens of billions, not hundreds of billions. That's the difference. Okay. Now that was doing it as a government program, a purpose-driven government program, as opposed to a vendor-driven government program. Because NASA has 2 different modes of operating. They have a purpose-driven mode in which they can be fairly efficient, and a vendor-driven mode which they can be zero efficient. Okay. And you've seen both. Okay. You see it in their planetary exploration program and space astronomy program. Those are purpose-driven programs, and their accomplishments have been epic. The human spaceflight program was purpose-driven during Apollo, but since then it's drifted and it has allowed itself to become vendor-driven, and where it no longer spends money to do things, it does things to spend money. And thus SLS, let me show you a little something about SLS. Look at this. This looks like SLS, doesn't it? I drew this chart in 1990. Because in 1988, I was a member of the Martin Marietta team that did the preliminary design for the ARIES, which is now what's called SLS. Okay, and this should have been flying by the mid-90s. Because when we designed this, we did not think that this was the most advanced launch vehicle we could design. We thought this was the most elementary way to bring about a heavy lift vehicle. Because all this really is the shuttle launch stack without the orbiter. But NASA turned this into a 30-year meal ticket program. Okay, it's 31 years, and it still hasn't flown. Okay, and if this had been introduced in the 90s, it would now have operated for a quarter century and be ready for honorable retirement with the arrival of Starship. Instead, this will be flying at most a few years before Starship arrives and makes it completely obsolete. Okay? It is out of its time. Okay? Now, there's a problem with the vendor-driven program and the monopoly relationship and cost-plus contracts where the longer they take and the more it costs, the more they make. Okay, these all lead to stagnation, have led to stagnation. Now the Renaissance, and this is, I have a new book coming out called The Case for Space, coming out next week in fact, and it talks about the entrepreneurial space revolution, how it has happened and the possibilities that it will open up for the human future in space, which are manifold. Okay, because the government space program has dropped the ball in the area of human spaceflight and space launch technology. Okay, they continue to accomplish a lot in planetary exploration and space astronomy. Okay, new players have entered the scene. Nature abhors the vacuum. And so you have these people saying, well, somebody's got to do it, I'm going to do it. Okay? And what Elon Musk in particular has proven is that it is possible for a well-led entrepreneurial team to do things that it was previously thought that only the governments of major powers could do, and not only that, do them in 1/3 the time at 1/10 the cost or less, and even do things that they had deemed fundamentally infeasible, like reusable launch vehicles that take off and come back to the pad and land. Okay, there it is. It's happening in front of you. And in the course of doing this, not only has he introduced and is continuing to introduce new and very attractive space launch and systems and capsules and so forth, okay, but he's proven this broader point, and so emulators are getting into the game. Blue Origin, Virgin Galactic, and not just them, but it's not just billionaires with play money. There are working engineers, people with no more means than you or I, who've managed to sell business plans to investors and have gotten $100 million, $300 million funding to create new launch companies like Rocket Lab. There's a New Zealand company, and they're reaching orbit. New Zealand doesn't even have a space program. Okay, and so this is also internationalized a thing in a way that was not the case before, where anyone can enter this. Why not an Italian SpaceX? Huh? How about it? There's no reason why this can't be done. Now, so this is happening, and now, okay, now as far as this is concerned, okay, from a technical point of view, we're much closer today to sending humans to Mars than we were to sending men to the moon in 1961, and we were there 8 years later. And that statement was also true in 1990. And if the political class had been serious, okay, if George Bush the first, when he announced the space exploration initiative, had been really committed to it, he could have had humans on Mars by 1999 using an approach like this. But they weren't. They were just talking stuff in order to appear to have some flair and, still have the same kind of stuff that John F. Kennedy had and so on. Okay, and so it didn't happen. Okay, and because the quality of the political class in general has deteriorated a lot since the 1960s, and also it has to be said of many parts of NASA. Because, a lot of organizations, this is not just true of NASA, but almost any organization you can think of, political parties, trade unions, they're formed around a cause. And they are dynamic, and they recruit people to them on the basis of their commitment to this great cause. But after a while, whether they accomplish the cause or not, the leadership's primary concern becomes preserving and growing the organization rather than accomplishing the cause. Okay, you see this in all different kinds of things in society that exhibit this behavior. And this has also happened a lot with NASA. So it was formed around the cause, reaching the moon by the end of the decade, astonish the world with what 3 people can do, and so forth. Then it becomes, how do we preserve the organization? How do we make sure we still have funding for the Marshall Space Flight Center or this place or that place? Okay. So they've become adverse. But here you have SpaceX building Starship. Okay. Already done Falcon Heavy. Now it's Starship. I believe Starship will be flying by 2024. Okay. And you'll have some of these other people introducing space hardware. Okay. So by 2024, the appearance of humans to Mars to the political class will no longer be of something that is off in the far future. It is, we have the capability of doing this. We can have people on Mars by 2028. Look at this thing, it's flying now. All we need is these few extra things. Okay, we need a Mars spacesuit. We need some other stuff. But the big things are already developed. We could do this during my term in office. We could do this during a time scale that's relevant to us. So let's do it. And so I believe that the combination of the entrepreneurial space race, creating the technology, and also simply the spread of the idea, which is becoming ever more pervasive in society, much more so than was the case in the 60s, for example, that a positive human future involves human expansion into space. Okay, those two things, the spread of the idea and the realization of the technology, I think nothing can stop an idea's time has come. This idea is already recruiting to its banner the forces necessary for its realization, and this is happening. Other questions?
Well, I'm quite convinced as you that will not be governments to lead us to the next steps of exploration, of climate exploration. But continuing your reflection to all the things that you have just said, one question would be, why people like Jeff Bezos, Elon Musk, or whoever will come in the future should choose for the next steps in exploration Mars instead of the Moon? And there is something that I still have difficulty to understand. There is this sort of, when talking about the future of exploration, of human exploration, there is continuous competition in Mars and Moon. We have some Mars, we have some Moon. We have already been on Moon, that's a fact, or whatever you want. Could it be a difficulty to try to understand or to put up a schema, a plan, a program where these two planets, these two objects can be in continuous competition, can be put together to elaborate an overall plan of exploration, which match together all the pieces, all the competencies, all the economic competition that will come in an overall framework?
Okay, that's a good question. All right. So, the reason why I prefer Mars to the Moon is because it's a much richer environment. The Moon, there is some water and permanently shadowed craters near the South Pole. In Mars, there's water all over the place. There's glaciers on Mars, as far south as 38 North, which is like Athens. There's underground water. There's continent-sized regions that are 60% water by weight in the soil. There's carbon on Mars, carbon dioxide atmosphere, 95%. We are carbon-based life forms. We're made of carbon. Everything we eat is made of carbon. Everything we wear is made of carbon. And in fact, practically everything we use is either made with carbon or with the help of carbon. There's nitrogen on Mars. There's no nitrogen on the Moon. There's no carbon on the Moon. So Mars compares to the Moon like North America compared to Greenland in the prior age of European maritime exploration. Greenland was closer to Europe. Europeans did reach it first. Vikings established outposts there. But it wasn't a place where you could establish a true large and vibrant branch of human civilization in the way you could on Mars. So that is why I prefer Mars, and there's additional reasons. Now, Elon Musk prefers Mars because he read my first book, The Case for Mars. I'm not kidding, he did. And Musk was a member of the board of the Mars Society for a while until he said, look, I'm the kind of guy who wants to do my own thing,
Well, not just that.
Okay, well, no, it's true. I mean, now Bezos different. I didn't recruit Bezos. Gerard O'Neill recruited Bezos. If you want to know what Bezos is thinking, read Gerard O'Neill's book, The High Frontier. Okay, and he has a vision of Earth orbiting space colonies funded by beaming solar energy down to Earth with solar panels made from lunar materials. And that's the vision that recruited Bezos. And by the way, in both of these cases, these are vision-led enterprises. They're not doing it to make money. Musk will probably make money with SpaceX because he can make money doing anything. Okay, I mean, look, he's making money with an electric car company. You know how many people tried making money with electric car companies before Elon Musk? Okay, it goes all the way back to Thomas Edison. Okay, Elon Musk can make a lot more money with a chain of candy stores, okay, than he can with SpaceX. He will make money doing it, but he is doing it to realize a vision. Bezos is, once again, is motivated by a vision. The vision is recruiting to its banner the forces for its realization. Now, in order for it to become self-sustaining, it has to make enough money to sustain itself, and I think that's what you're seeing with SpaceX. Now, in terms of Moon or Mars, so long as this is a government program where you have to convince a certain political leadership what is our objective, And they say, well, choose. It's this, it's that. Okay, so the Trump administration is choosing the moon. The previous Obama administration, Charles Bolden's position was, we will never go to the moon. That's why he proposed the deep space gateway, which the Trump administration is not maintaining as necessary to go to the moon, even though it was conceived of for the purpose of not going to the moon. But but put that aside. You have a party line, you have a party position. With an entrepreneurial-driven space program, we can have multitudes of objectives. Okay, not everybody has to agree. Okay, Musk is focused on Mars. You walk into SpaceX, you see on the wall a gigantic photograph of Mars, and every employee walks past that photograph every day, going in and going out. That is the objective of SpaceX. Okay, once again, Bezos is focused on the moon. We can have, different objectives embraced by different groups, and a much more creative and dynamic program. My position is not that we shouldn't go to the moon. My position is that we should go to Mars. Now SpaceX, okay, Musk, unlike Bezos, does not have unlimited funds. He has substantial funds, but he doesn't have unlimited funds. Okay. So what he's doing is he's developing parts of his required hardware set by addressing needs that NASA has, supply the space station. He will undoubtedly show the utility of the Starship in supporting the Trump lunar initiative. Okay, so he's crossing the river by jumping from stone to stone, providing the stones are in the general direction of crossing. Well, that's my answer. I prefer Mars for the reasons I gave. Musk also prefers Mars for those same reasons. There are other people who have other preferences. And with an entrepreneurial space industry, multiple objectives can be pursued and will be. Other questions? Sir?
Could the hypothesis of finding life of Mars slow down human settlement on the planet?
Well, there are some people who have that position, not only that it could, but that it should. Okay, I think that these are false arguments. Okay, that is an argument that I sometimes hear is we shouldn't go to Mars with people because if we do, we won't know if the life we find on Mars was there before us. Okay, well, how do I know, coming from America, that there were people in Italy before I got here? You could have all just shown up. You might have gotten off the plane behind me. But there's all these artifacts around here. There's this building and also some buildings in Rome that are substantially older. Okay, there is proof that there were people here in the past. If there is native life on Mars, by definition, it was there in the past. It will have left fossils and other biomarkers. If you go to Mars and find life and it is native, there will be biomarkers. Okay? So that will be, even if the life is identical to Earth life. If you find E. coli on Mars, but you find biomarkers that it was there in the past, then you didn't bring it. Okay? If you find life on Mars that's different, if you find a different genetic code or even different forms, then you didn't bring it. But if you find life on Mars that's identical to Earth life, and there's no evidence that it was there before you arrived, then you brought it. Okay? So I think that's a false argument. People do advance it. I compare it to the creationist argument. In the United States, there are religious fundamentalists who argue that the fossil record does not prove the existence of the prehistoric past, because God could have created the earth with the fossils in it. Okay? And when he created the earth, he could have put these trilobite fossils and dinosaurs, he could have done it to test our thing. Well, what can one say? Okay, it's a crazy argument. And for someone to deny that if you found biomarkers of life on Mars, that it wouldn't prove that the life was there before you, it's essentially creationism. Other questions? All right, well, let me just mention a couple of things. Mars Society is an international organization. Our next international conference will be in Los Angeles, October 17th through 20th, at the University of Southern California. I actually have some flyers here for it, and there's even an open call for papers if you'd like to present there. Our next European conference will be in London in around November 3rd through 6th, and I think if you go to the Mars Society Italia website, there is information about that. Okay, so thank you very much.